This time I want to introduce two very important results known as the initial and final value theorems. So without further ado, these are the theorems. The initial value of the step response, that's the value just after the step has arrived, is equal to the frequency response evaluated at infinite frequency. And the final value of the step response, that's the value after an infinite time when everything has settled down, is equal to the frequency response at zero frequency. Now, I'm not going to give you a formal proof of these theorems here. You'll come across that later on when you start studying Laplace in more detail. However, I can give you a justification for them and something that will hopefully give you a way to remember them. And this justification goes as follows. Supposing we have a circuit with an input here, A of t, which is going to be our unit step, and that goes into a network which is some combination of resistors and inductors and capacitors. I'm drawing one that's intentionally rather complicated, and more complicated than any one that we're going to be working with. But let's suppose we've got something like that, and we want to find out the step response of this network. Right. Consider what happens just after the step has arrived. Well, just after the step has arrived, the voltage across the capacitors must be zero, because the voltage across the capacitors just before the step arrived was zero. Because remember, definition of a unit step, it's been zero for all time, all infinite time, up until when the step arrives. So there's never been any voltage anywhere in this network before the step arrives. That means that the voltages across the capacitors will have been zero just before the step, and therefore must still be zero just above the step. Well, if the voltage across a component is zero, then that component is effectively behaving as if it has a zero resistance. It's behaving just like a wire. The inductors. Just before the step arrived, there is no current through any of these inductors, because there are no voltages or currents anywhere in the network. And therefore, just after the step has arrived, there will be no current flowing through the inductors either. Well, if there's no current flowing through the inductors, then the inductors are effectively behaving as if they have an infinite impedance, since that would not allow any current to flow. Well, the complex impedance of a capacitor is 1 over j omega c. So when the frequency is infinite, the capacitor is behaving like a wire. It has no voltage across it. And the complex impedance of an inductor is j omega L. So at infinite frequency, this behaves like an infinite impedance. There is no current flowing through it. But that's exactly what happens just after the step arrives. No voltage across the capacitor, no current through the inductor. So the circuit, just after the step has arrived, behaves exactly like the circuit, with an infinite frequency flowing through it. And that's all the initial value theorem says. The circuit is behaving just after the step response arrives, as if the input was an infinite frequency. For the final value theorem, you could note that after everything has stopped changing, there will be no current flowing into or out of the capacitor. And if there's no current flowing into or out of the capacitor, then the capacitor is effectively behaving like an infinite impedance, which is exactly what it has when omega is zero. And after an infinite time, when everything has settled down and no currents and voltages are changing, there will be no voltage across the inductor. So remember, the voltage across the inductor is L di dt, related to the rate of change of the current. if the currents are no longer changing, there will be no voltage across the inductor. If there's no voltage across the inductor, it's effectively behaving like a wire with a zero resistance, which is exactly what an inductor does at zero frequency. So after an infinite time, when everything is no longer changing, the capacitors effectively look like infinite impedances, the inductors effectively look like zero impedances, just as the components do at DC. So, final value theorem says that the final value of the step response is the frequency response at zero, and the initial value theorem says that the initial value of the step response is the frequency response at an infinite frequency. Where the x's are functions of time and the h's are functions of frequency. Now, once you know the initial value and the final value, both of which are quite straightforward to work out from the frequency response, for any first order system, you can then write the step response in terms of the initial value, the final value, and the time constant. There will only be one time constant because there's only one pole in the response. And I can write the general form of the step response of a first order system in this way. It's the final value minus the initial value times e to the power of minus t over the time constant. And that works for any first order network and can save a lot of time trying to do integrations and sort out the correct values of the integration limits. Now armed with this technique, we'll have a go at the other two cases of first order step responses.